Welcome back. In this lecture we will discuss preparing data. Here's our lesson objective. Okay, so the first way to think about preparing data is feature scaling. So you will be looking at data where you'll have different feature values for each of your samples, and often is the case where those values will be on different scales. So in many cases, it would be a good idea to kind of get them on the same scale, especially if you're using something like a non-parametric approach, such as k-nearest neighbor, or a model like k-means clustering that's dependent on a distance function. So first is range standardization. And so this is for quantitative values that follow generally a linear scale. And what this is doing is putting everything that, making all your values go from 0 to 1. And it looks like this. So given a sample that has value x, you're just subtracting from it the minimum value over all your samples for that feature, and you're dividing it by the maximum minus the minimum, and this gives you your standardized value for that feature. The next is a z-score. And this transforms your data to have a mean of 0 and an absolute deviation of 1. And so if you have a value x and then the mean of all the feature values is mu and standard deviation sigma, we simply use this formula here. And you see it kind of resembles standardization, except you're using mean and standard deviation as opposed to minimum and maximum. Now, what if you don't have linear scaling and you have something like a power law? Well, you probably want to embrace what's called logarithmic scaling. And one example of this is you could think of terrorist attacks in the United States. 9/11, you had over 2,000 people were killed, and that is order of magnitude greater than kind of the next largest terrorist attack that happened in the U.S. And so the scale, or so this follows a power law distribution, and power law distributions occur in many things in nature. And here we have it based on protein interactions relating to presence of pathogens. And so we look on the x-axis as the number of protein interactions and then the average number of pathogenic interactions. Notice that this scale, we see a linear relationship, but the y-axis is not evenly spaced. We go from 0.01 to 0.04 to 0.16. Those are all evenly spaced. And that happens because the y-axis is logarithmic, which allows us to get a nice linear regression model. If we did not have logarithmic scaling, you would see a very skewed line, and it would be tougher to fit to a linear model. The next method for preparing data is clipping. And so here we see some box plots. This deals with looking at a certain type of measurement for identifying users that were either active on Twitter or became inactive due to being barred. And as we know in box plots, these whiskers represent a small number of samples. And so with clipping, we would just set the range to be within a certain number of standard deviations from the mean, and everything outside of that would be sort of set to the values either at the upper or lower end of those boxes. And this is a way that also helps reduce the effect of outliers on data. So with nominal features, so now we're getting into categorical data, there's no ordering, so it's really difficult to give them a numeric value. So one way to do this is replace them with binary values, and one for each category. So if we have our iris flowers of 3 different species, and let's say if this was a feature, so the feature could be species, it has 1 of 3 values. Well, we can now replace that with 3 features where each has either a 0 or a 1. And so depending on what species it is, so if it's, say, Setosa, The first feature value would be set at 1, and the other two would be set to 0. Ordinal features. One way to treat ordinal categorical values is to assign them values based on the order. But note, this does not consider the scale. So now we have young, teenage, adult, and senior. We transform this to 1, 2, 3, and 4. So this concludes our lecture on data preparation. Please stay tuned.